So today we are going to start our PLL series. So this will be our first series on PLL, where we will go through the basics one by one in each series. So in this series, I am giving a brief summary about each blocks of PLL and what a PLL is. So my contents will be arranged like this: why we need a PLL, then what are its block, VCO, crystal oscillator, frequency divider, PFD, charge pump, loop filter, and later on we will summarize the complete PLL architecture. The first series is why every RF system needs a PLL. So basic RF example can be our mobile phone which we use daily. So our mobile phones uses uh, various ranges of frequencies depending on the generations we use or technology. Suppose 2G uses a 900 megahertz, whereas 4G uses 2.6 gigahertz for fast internet. And nowadays 5G millimeter wave, which is extreme speeds which are used by defense personals. So our air is basically slotted in different fragments to support our wireless communication. So how that frequency is getting tuned to our device, that is where PLL comes. So our device needs a PLL to tune ourselves with a particular range of frequency. So next slide is what is VCO. VCO is one of the most important part of a PLL, and you can say it as a brain for PLL, just like our body has a brain. So what a PLL is? Sorry, what PLL I explained. Now what is VCO? VCO is voltage controlled oscillator, which means for a given input voltage, which is for in this example you can say VDD. So for a given VDD, the PLL will the VCO will generate a frequency, a frequency based on input voltage. So how that frequency is generated? So if we suppose the delay of each, this is a basic example of oscillator. It can be a LC oscillator. So here we have taken a ring oscillator, for example. So each of these three stages have a delay TD. And for this case, if you will go into Barkausen criteria, then you can recognize why we need only minimum three stages to have oscillations. So if we suppose n as the number of stages where n is 3 for this case, so frequency of oscillation will be f equal to 1 by 2n into Td. How it comes, we'll go through this whole cycle. First I can explain. Suppose the initial stage of inverter C is 0. Okay, so from C, so this is the C waveform. If my screen is visible cursor, so C is 0. So from 0 to 1, there is a transition. During that transition, how the other signals behave means output of A and B. Suppose C was initially at 0 and it jumped to 1. In that case, A will take a delay of TD. So A is still at the initial position, but it has got this signal C. But the C will trigger after a delay of TD, but A will be triggered after a delay of TD. Okay, then B will be triggered after a delay of 2TD. So, in that sense, each of these stages will be triggered by a certain delay. So, finally, to reach this whole oscillation, it needs a cycle of 2TD. So, total cycle for one period. Frequency is what? It's inverse of time period. So to take one time period of oscillation, it takes a 2 TD time. And depending on the number of stages, that time period will be increased. So our case is for 3. So total time period will be 2 into TD into number of stages n. So inverse of time period is frequency, which we can see frequency is 1 by 2n TD. Now, here in this case, this VDD is fixed, but for actual practical PLL case, VDD is not a fixed case because we want more controlled oscillation. We want to tune our frequency based on the bands which is required. So, in order to achieve that, we need a VDD which is controlled, which is not fixed, because we need a frequency control. So next thing is to control this VDD. How is VDD controlled? So we will replace a VDD with a current source, and this current source will be controlled by an external voltage source. So we'll add, in this case, since we have added a current source, this will not only reduce the frequency, but it will not only reduce that charging time to charge the caps and uh, oscillate, but also it will increase the frequency. How? Since the capacitors are getting charged faster, the frequency of oscillation also increases. So that is our requirement, because from PLL we want a frequency in a range of gigahertz. So to achieve that, we need to have a source which switches so fastly that it will be able to achieve that frequency. So that is only possible with a current source. So this kind of oscillator is called a current controlled oscillator. But yeah, if this current is not constant, it is varying, then in that case we will see a glitch on the edges of this was our square wave. So if we'll not have a perfect constant current source here, so our edges, rising or falling edge, will have a glitch, which is the most important parameter to be taken care during design, because glitch or phase noise is very much important parameter to be looked into before designing any VCA. Another thing is, we should always ensure that the MOSFETs inside these inverters should be in saturation, so that these currents are constant and in return the voltage is constant at each node. Next thing is how that is achieved, how we achieve a current control source. So this is our controlled voltage we control, which goes, this is a basic uh, current mirror, you can say, where control voltage is input to a GM device and it mirrors the current. It mirrors the current generated because of V control, and it mirrors into another branch. So this whole block we can call a V2I, which gives current I to a CCO, which we have discussed in last slide. So this whole V2I plus CCO is called VCO. Okay, so VCO have a control voltage as input and a frequency which is in megahertz to gigahertz range as output. So VCO consists of broadly two branches, a V2I and a CCO. How constant current is generated from V control? So one of the most important thing is this should be a cascade network, because there are some supply noise from LDO. And so to cut that and to have a very good PSRR, we should make it a cascaded. And if noise comes from the DC source, it will also create a jitter, which is again a problem, as I told. Jitter or phase noise is one of the most important parameters to be taken care during designing of VCUs, which we will discuss later. Although, okay, so this V2I is usually designed using IO devices, and this CCO will be designed using core devices. So CCO can be any kind of oscillator, be it ring or LC oscillator. But mostly in our case, we have considered it as ring oscillator. But if jitter is the main consideration, then we will use LC oscillators in place of CCO. Means CCO can be a LC oscillator or a ring oscillator. Next thing is crystal oscillator. Okay, so as I told, there is a VCO which has input as V control and it generates a output frequency. So can we directly use a VCO? Question is that can we directly connect a VCO in our phone to generate 3.5 gigahertz of frequency? Yes or no? Answer is yes. If we will get a stable voltage V control, if it is very stable, it is very clean, then we can get. Then we can only use VCO and there is no need of other blocks. But it is not possible in practical case. We cannot get a controlled and clean control voltage, so we cannot use VCO directly. So for that we need another reference or standard oscillator circuit, which is called crystal oscillator. The crystal oscillator generates a very high precision frequency, but the frequency is very low. So from that frequency, we are going to generate a very high frequency, which is needed in our RF applications. So crystal oscillator is used as a reference to generate a very high frequency. So again, yeah. So what are the demerits if we'll only use VCO? Is PVT variations of control voltage. Then frequency tuning is not possible only with VCO. VCO will always generate a single oscillation frequency, but in our practical RF application, we need to tune the frequency depending on our applications. Another demerit will be synchronization. Synchronization with the reference or base station. Suppose we are doing a RF communication, so we have to synchronize the frequency of base station and our mobile station. So that thing also will not be possible if we are going to use only VCO. So we need a negative feedback system to do this job. So we'll discuss each of these blocks in the feedback system one by one. So our first question was, can now we have crystal oscillator and VCO. So crystal oscillator is reference for VCO. So now my question is, can we directly use only crystal oscillator and VCO? No, because VCO's input is control voltage, but output of crystal oscillator is a frequency. So we two different. We cannot since we need input to VCO as voltage, but output of crystal oscillator is frequency. Frequency cannot be fed to VCO. So another thing is crystal oscillator generates a very low frequency, and yeah, that is the role of crystal oscillator. It guides our main VCO to generate a high frequency and very stable high frequency. That's all. So crystal oscillator gives only frequency in kilohertz to megahertz range, whereas VCO will give frequencies in megahertz to gigahertz range, which is our required application. But we need something between VCO and crystal oscillator because the inputs and outputs are different. Okay, so next slide. What is required? Since I told crystal oscillator gives a frequency of kilohertz to megahertz range, and VCO gives frequency of megahertz to gigahertz. So we need to convert this megahertz to gigahertz back to kilohertz. That is down conversion so that it can be fed back to our uh, crystal oscillator. So crystal oscillator gives a reference clock, whereas the frequency divider gives a feedback clock to VCO. So now there are two frequency inputs to VCO. One is from crystal oscillator, another is from frequency divider, which is called feedback clock. So now two frequency inputs are given to VCO. And as we know, VCO cannot take frequency inputs. It can only take a voltage input. So here comes the role of PFD. What is PFD? PFD is phase frequency detector. What PFD does is it detects the two frequencies which is input to VCO and compare the frequency and generate the a voltage on the basis of comparison. So now next question is, if it is really a comparator job, so why can't we use an analog comparator instead of using a complex PFD architecture? Why can't we use only a simple analog comparator? The answer is we cannot use an analog comparator because analog comparator only compares voltages. But here we need to compare frequencies. Okay, so next slide we will just basically look the basic role of PFD because it is one of the most important block. So a basic PFD block will look like this. So input to PFD is a feedback clock and a reference clock, and output is a up signal and down signal. Ideally, this down signal is very small because once this AND gate comes high, it will reset this flip-flop and mostly it will be in low state. So that is our required. Based on this delay of a AND gate, we have different architecture of PFD. So let's explain the working of this. So we have a reference clock and a feedback clock. As I told, there are two inputs to VCO, a reference clock and feedback clock. So reference clock and feedback clock are input to VCO, but we need VCO input as a voltage. That's where comes the role of PFD. So PFD is between VCO and these two inputs. These two inputs are coming from where? This reference is coming from crystal oscillator. Feedback clock is coming from frequency divider. So we need to compare these two and generates a voltage. So depending on, see, the reference clock comes first and feedback clock comes later. This can be reversed depending on our use cases. So for this example, I have taken reference clock as first incoming clock and later feedback clock comes. Since this reference clock is coming and it is going to AND gate, our this D flip flop job is just like a simple buffer. If clock is at high, then it will pass 1. If clock is low, it will pass 0 or nothing. Or you can say memory state. So first is reference clock. Since reference clock went high and our D was already in one state, so this up signal went high. Okay, as soon as this feedback clock went high, goes high, this AND gate output becomes 1. So when this AND gate output becomes 1, then at the same time these flip-flops get reset. Means up signal got reset to 0. So in that case, this lower flip-flop will never get a chance to get up signal. Only in the case where reference clock comes later than feedback clock. So this, for suppose this case, here the reference clock is behind the feedback clock. So here feedback clock is active. So in this case, down flip flop become active and it will give a pulse. So based on this, so mostly our target is to lower this down signal or lower the delay of this AND gate. If the AND gate delay is lower down, then our output DN output will be almost 0 or DC, because before coming to this pulse state, this AND gate will go and reset the flip flop. So it will never come into this pulsated state until unless the delay is very low. That is not our requirement. We need to make the delay of this AND gate as low as possible, depending on our design architecture. so that this DN signal will almost come to zero. I'll explain you why we need a very low DN signal, or why we don't need the pulse in DN signal. I'll explain this later. Okay, so next job is here. Here comes the role. So this up signal is a pulse signal, okay, but our control voltage again cannot be a pulse. It should be a continuous stable DC voltage. So this up signal is going to these current sources, which we call as charge pump. Okay, so up signal is going in the upward terminal, and this upper terminal is connected to a VDD source, suppose. So whenever this up signal is on, it will charge the capacitor. Again, this capacitor is a loop filter which will only pass the low pass signal. Okay, so this all DC sources is going and charging the filter. Why I told is we don't need a pulse in DN signal is, if the pulse comes to DN signal, it will discharge our capacitor. Okay, so it that also can be the case if we need a suppose a lower voltage or lower control voltage. So the voltage can be discharged. Suppose we need a higher control voltage, then up signal is up and it will charge the capacitor. So based on our use cases, the capacitor gets charged or discharged, or based on the frequency which we want to tune. On that basis, this voltage is controlled across the loop filter. So now we have come to an end of our basic PLL discussion, and here is the full architecture which I have explained already. So I have explained VCO which is one of the most important building block of any oscillator, which generates the output frequency. And input to VCO is a control voltage. So this F output is again divided by a divider and feedback to PFD. So this PFD compares the reference and feedback clock, which in turn generates a up signal and down signal. So based on this up and down, this charge pump will generate a current, and that current is converted to voltage by a loop filter, which also filters the other unnecessary harmonics and only gives a filtered, stable, clean DC voltage as control voltage to VCO. So this whole loop functions in order to get a clean and stable control voltage to generate our output. And this can be tuned based on our requirement. So this control voltage is always a tunable thing, which is what makes PLL different from normal oscillators, which where we don't have control. I hope this discussion was very useful. And here we come to end of our first session. Thank you very much.